Hello everyone. Today I am here to describe the topic of computer networking, that is called MAC protocols. From where this name derived, MAC protocols. Basically we need to focus on 7 layers of OSI model, where there is a second layer called data link layer, and that data link layer as per the IEEE standards is divided to two parts: logical link layer and MAC layer. This link layer is responsible for error control and flow control, and now our main focus is on MAC, that is media access control. The question of controlling the media arises when we talk of computer networks and we make use of a shared medium, and that shared medium is represented in this diagram. Means we are connecting different systems together in a LAN, that is local area network, Ethernet network that is called, and whenever any station wants to transmit data, it may or may not collide with the data being transmitted by other systems. So we need to ensure, this is the basic requirement, that why we are studying this need. Why it is needed? Because we are in the era of networking. We need to connect different systems, and first of all we need to ensure that in LAN, in local area network, if we are using a shared medium, then how we can control accessing the medium. So the protocols are defined, different categories of protocols are there. Out of those categories, they are listed here: random access, controlled access, and channelization protocol. The scope of discussion in this lecture would be on random access, that too on the specific topic Aloha. This is the first algorithm of random access category, which assumes certain points like whenever a station wants to send information, there is no control on that transmission. Any node at any time can send the frame that may be received by other on the network. But why it is random? There is no concern whether the frames collide or not. Blindly they are being transmitted, and whether they are received properly or not, that is the luck of these nodes. So that depends how many attempts are there in particular transmission, how many attempts we are making. A particular node A is making an attempt to transmit to other nodes. In that particular interval, this particular node A is transmitting. If no other device is transmitting, then that frame will be received by all the other nodes intact without any collision. But that is not the case always. So the first and the simplest algorithm was random access, where we don't have any control. That's why the name was given as random access protocols. Now in the first category, I'm going to focus on Aloha. I have discussed till now the MAC layer, need of this protocol, and the classification. There are a number of protocols under this classification, but our focus in this lecture would be on Aloha. Now this is basic working of Aloha protocol. Like there are some questions that should be asked, like what this protocol will do if this message gets collided, and how to detect that there is a collision, and if there is a collision, then how to handle that situation. So that's what these are rules, that is protocol, set of rules to govern the communication. So how this Aloha handles that situation, that is explained in this flowchart. In this flowchart, we start the transmission. In this scenario, any node starts transmission. This variable k is mentioned here. What is k? This k in this scenario represents the number of attempts for transmission, because maybe the first attempt is successful or it is not successful. The second attempt would be there. Let's suppose we try to exit out of a door which is very congested, and everyone wants to go out from that way. In that case, if there is a discipline among the members, they make a queue, they go one by one. In that case, the possibility of congestion at the door would be less. By 1 minute or 2 minutes, everyone will be outside. but if there is no discipline, randomly they want to go outside from a congested door, then there is a more possibility that some of the people will getting hurt, or they will not be able to go outside. So in that case, there should be provision, there should be a discipline that if someone is not able to go outside, then what should be done. In the same sense, we have Aloha. In that case, what we do if there is a collision. Now let's suppose two frames start transmission at the same time, they get collided, and again they try to transmit the data simultaneously, again they collide. Then what should we do? What should be done? In that case, we are incorporating a step through this flowchart of this algorithm, that is basically Aloha protocol. Initially we send the frame and we set the count of attempt, that is 0. This count 0, with this count 0, a frame is sent and we wait for acknowledgement. Now what is the need of waiting for acknowledgement? Because every frame takes some time to be transmitted from one place to another. That time depends upon the size of the frame, and depending upon the size and depending upon the bandwidth of this channel, the time will be decided. This is the time that this node will take in order to transmit that amount of data from this interface to the channel, and depending upon the size it will take some time. That time is called TFR, that is called frame transmission time. This frame transmission time amount multiplied by 2, or we can say propagation time multiplied by 2, is the time during which a node should wait for acknowledgement before trying another attempt. So this is the minimum time that will be taken by the frame to reach to the other node. So that's why this is the waiting time for this node after transmission. Now after this time, whether this node receives acknowledgement, a special kind of frame that is received on the node after successful reception of the frame, that is acknowledgement. If it is received, yes, there are two cases, yes or no. If yes means success, the frame is finally transmitted, but there is less possibility of this yes. There may be collision. At the same time other nodes may be there, they may be transmitting, because of that there will be collision, and in that case again that node needs to send again the frame. That is called retransmission policy of this algorithm. Obviously we need to send data which is lost, so we need to retransmit. It will reduce the efficiency of the channel, but this protocol handles the situation in this way. It increases the attempt number k++. After this attempt number, there is again a provision in this algorithm that how many times a node should attempt, or it will make the bandwidth unutilized. Like every time there is a requirement of retransmission, then what is the use of this algorithm? Or that node should be stopped transmitting the data. That condition is posed by this point k, that is the fixed number of attempts that a node can make in order to transmit. That if that limit is exceeding, we should abort the transmission. If it is not achieved, then we can go ahead, means there are some more number of attempts left to make the transmission. Now let's suppose we say that this node should wait. By how much time it should wait? Maybe other node is waiting, and the same time they wait for the same amount of time, means they will again collide. So in order to have randomness among the waiting time, we introduce a random variable r, that would be between 0 to 2 raised to power k minus 1, where k depends upon the attempt number. So more the number of attempts, more will be the randomness in this variable. More random variable will be chosen, and there will be less possibility that the waiting time would be same for simultaneously transmitting nodes. So by taking that value, we take into account BT, that is back of time. This is the time during which a particular node who was not able to transmit should wait, and then after that amount of time is complete, again make an attempt to send the frame. In this way this cycle goes. So I'm not saying that this Aloha protocol gives 100% efficiency. That we will be calculating that what is the efficiency of this Aloha protocol. Actually there is a 100 Mbps line, but whether actually we are transmitting 100 Mbps data? No, because still there are some retransmissions, still there are some collisions. So what is that amount of collision? We'll see again. After understanding the basics of Aloha, we are focusing on types of Aloha protocols. The first type of Aloha protocol is pure Aloha, and the second type is called slotted Aloha. Now depending upon how much time we are given for transmission of frames, we have this classification, pure and slotted Aloha. We'll discuss about vulnerable time of these two protocols. Now what is a vulnerable time? The time during which if transmission is done by only single channel, then there will be no collision. This is a kind of guarantee, a time during which only one node is there which will transmit the data. In that case, there will be no collision. So, as you can see from this diagram, these are the examples of two nodes transmitting the frames. In this case, the frame is being transmitted after T naught time, not exactly at T naught time. After this T naught time, the difference between T naught to T naught plus T is the time of frame transmission. Like one frame takes this amount of time and every frame needs the same fixed amount. And in this case, as there is randomness, any node can send the frame at any time. So if we allow this transmission just after this frame transmission time, and after this transmission has started, during this interval from T naught plus T to T naught, if any other node starts transmission between this T naught to T naught plus T, then there is much awaited possibility that later on at this point of time, these two frames are going to collide. Similarly, when at T naught plus T time this frame has started transmission and it has to take T time for completion, but before completing that T amount of time, another node again transmits the frame. In that case again there will be collision of time, like the frames, the data will be collided with each other. That's why both the frames will be vanished. There will be no meaningful information among these two frames. So this is the case when there is a sufficient gap between the frame transmissions. This T naught plus 2T time, and after this T naught plus 3T time, this frame is transmitting, this particular node is being transmitting this frame, and there is no collision with the transmission of other frames. That's why this is being successfully received. So what is that time? We can see from this diagram, if any node wants to send data, there should be no node sending the data before T amount of time of the start of the current node and after T amount of time of the start of the current node. So that will be total of 2TFR time that should be avoided for transmission by other nodes. So this is called vulnerable time of pure Aloha protocol. Why this is 2TFR? Because there is no restriction, randomly any node can transmit. We are not stopping the transmission, but we are calculating the vulnerable time. If it is possible that we can avoid the transmission during this time, we can have more efficiency, more throughput of the pure Aloha protocol. Now, if we talk of this pure Aloha, how to calculate the throughput? As it is discussed in the previous presentation, like there is randomness of transmission. As there is randomness of transmission, we can use Poisson distribution function to know that how many attempts are possible in unit time. That you need to count the number of attempts. If there in this particular formula, K is the number of attempt, G is the average load given to the channel. Like this load may be given by any of the node in the network, but that is termed as G, average load per unit time. And this simply a Poisson distribution formula, e raised to power minus Tg means T is the interval parameter, what is the vulnerable time in that particular case, or what is the actual interval during which the transmission is being done. And G again the average load, K factorial is the number of attempts, successful transmission you can say. Using this formula we can derive throughput of this pure Aloha algorithm. Now how we calculate? If G is the load, means how much data we are giving to the network, that is G. Like if we are sending some person to go other place and that person is actually going there or not, that depends upon what was the congestion on the way. So in order to calculate that congestion, in order to calculate the possibility of retransmission or possibility of collision on the way, we assume that there should be no collision at least during the vulnerable time. So actually we are transmitting G. What is the probability that there will be zero other transmission other than this actual node that may be used in order to find the throughput? Now this average load is being multiplied by that probability that there will be no collision, no transmission by other nodes. Means we can use this formula: 0 frame transmission in 2 TFR, that was a vulnerable time. Vulnerable time 2 TFR, 0 frame transmission means no transmission by other. We can use this formula by putting the value k equal to 0. Here k may be 0. This G as such, and this T is vulnerable time, that is in this case 2. Putting these two values, G raised to power 0, E minus 2 G, 2 was replaced by T, and 0 K, that is 0 factorial, again 1, G raised to power 0 1, but we will get E minus 2G. So finally we get the throughput formula for pure Aloha, that is G into E raised to power minus 2G. Now what is that value of G if we apply in a network in order to have maximum efficiency? That is the formula for general efficiency. This general efficiency can be used, like if we are knowing the parameter G, we can calculate the efficiency. But a question may be asked, at what point of load we can get maximum efficiency? For that we can differentiate this expression with respect to G. While differentiating, we'll get that value of G, that is being calculated here. G is equal to half, that is G is equal to 0.5. So this 0.5 or half value means if every node transmits half frame during 1 TFR, then there is a possibility of getting maximum efficiency, and that maximum efficiency we can calculate by putting the value in this formula, that is G 1 by 2 S is equal to G 1 by 2 E raised to power minus 2 into 1 by 2. This is cancelled out. 1 by 2 into E minus 1, that is equal to 1 by 2 into 1 upon 2.71, that is around 18.4%. This is the efficiency of 18.4. You can see what is the actual use of this algorithm. 18.4 times data is only being received if we are sending 100 units of data. That is the efficiency. So this algorithm is not as used as we use slotted Aloha. What modifications we have done in this slotted Aloha? We have introduced some control. That control in terms of when a node can transmit the data. Some randomness is reduced. How? Every node has to transmit the data again randomly, but at a specific interval. There is a fixed amount of time during which every node can transmit. But if that at the start of that time any node is not ready to transmit, then during that particular period, no other node can transmit the data. So after the completion of this period only, other node may transmit the data. So it reduces the chances of collision. How? If there is a possibility of retransmission by 2 or more nodes in the same start time, then there is possibility of collision. Otherwise, if any node tries to transmit in between this interval, there will be no collision. So this slotted Aloha takes certain fixed time during which we can transmit the data, and accordingly in this case the vulnerable time will be reduced to half of the pure Aloha. Why? because this is the only time where we need to stop the transmission by other nodes. Other nodes, if are not transmitting, then this is a vulnerable time. After this time, any node can transmit. So vulnerable time is being reduced from 2 TFR to 1 TFR. If we use this value 1 TFR, like again we calculate throughput for slotted Aloha, we can modify this calculation. For slotted Aloha, what will be the changes here? Again G, some load is being offered to the channel, no collision during vulnerable time. Vulnerable time in this case is TFR, 1 TFR. Now G raised to power 0 means 0 frame transmission by other, same, this would be same. T value, now previously it was 2, now it will be 1, that means minus G upon 0 factorial, again this will be replaced by. So finally this formula will be changed for slotted Aloha. In pure Aloha, the efficiency formula was G into E raised to power minus 2G. In this case, we are getting it G into E minus G. Why? Because the vulnerable time is reduced. Now, similarly, if we want to have that amount of load which should be offered in slotted Aloha in order to have maximum efficiency, that can be calculated by taking the differentiation. In that case, these value will be changed. Minus 2 would be minus 1. This would be minus 1, this would be minus G, and the value will be 1. G value will be 1. So in this case, the efficiency would be twice as that of the pure Aloha. If you calculate in the same manner, the efficiency of slotted Aloha would be 36%, around 36%. So it is better to use pure Aloha by introducing some restriction on the time during which other nodes can transmit. So this is basically start of the classification of MAC protocols. Later on presentations, I will discuss other classifications of MAC protocols like channelization and controlled access protocol. Thank you very much.